Yeah, good morning again. Today we're going to talk about section 5.3, binomial probability distributions. All right, 5.2, we introduced the concept of probability distribution, and there are many types of probability distributions, and the binomial probability distribution is a very special one that we're going to encounter here. Uh, Motivation. Find the probability of, let's say, two girls in three births. All right, we've pretty much done this example to death, and certainly we know we've got 8 outcomes from listing our sample space in a brute force method. And if you've got two girls, that means two girls and one boy. You've got 3 slots available for that one boy, and so we get a probability of 0.375. All right, that's easy enough when you've got small numbers of events to deal with here. Suppose I was to ask you this. Find the probability of 50 boys, or 50 girls, let's say, in 100 births. Well, right away we got problems. If you think about 100 births, well, that means you've got 2 to the 100th power possible outcomes, and I don't even think our calculator can handle 2 to the 100th power, at least not easily. So we need a formula that can handle situations like this without listing the sample space in a brute force method, right? And there is a binomial probability formula that we're going to talk about today in this section. But we're getting ahead of ourselves. First, we've got to get some notation down. And we're going to say this: a binomial probability distribution will arise from a procedure that has the following characteristics. Well, you've got a fixed number of trials. Well, in a way, our problem types where we're seeking probability of 3 boys and 4 births, whatever, 4 would be our number of trials here, just like a number of children in that type of scenario. Requirement 2, the trials must be independent. And certainly when we're counting up number of boys or girls in a certain number of births, we're assuming independence and that the gender of one child in any birth does not affect the gender of a child in another birth. 3, there's 2 outcomes per trial. And that's where the bi in binomial comes from. 2 outcomes per trial, typically labeled a success or failure. And requirement 4 for a binomial probability distribution, the probability of success or failure, of course, remains constant in all trials. So if I ask you for the probability of, let's say, of 40 boys in 50 births, well, I claim this is a binomial experiment that yields a binomial probability distribution. You got a fixed number of trials. The gender of any one child is independent of another child. There's 2 outcomes per trial, typically boys or girls, and the probability of success or failure remains constant. Usually in this context, we assume boys, girls, equally likely. All right, so in some ways we've already talked about binomial probability distributions. Let's get some notation down. I'm going to let S denote the event of a success, and cap F denote the event of a failure. Remember, it's either success or failure in any trial. I claim the probability of success. I will let lowercase p denote the probability of success in any one trial, and the probability of failure in any one trial I will label Q, and of course, because there's only 2 outcomes per trial, Q equals 1 minus P. We're going to let lowercase n equal the number of trials in our binomial experiments, and X will be the number of successes that we seek in those trials. So let X equal the number of successes in n trials which we seek. Right? So the probability of X is then the probability of X successes in n trials. Alright, I'm going to invoke now this binomial probability formula. I kind of hinted earlier that there is a formula we're going to be developing today. Binomial probability formula. Well, let me label it like so. I'll claim it's the probability of X successes in n trials. I claim it's n choose X times P to the X times Q to the n minus X. Alright, now I think you can see here this accounts for the probability of a certain number of successes. This quantity here, Q to the n minus X, this will account for the quantity of a certain number of failures, and this n choose X, this is a combination command that our calculator works out that gives us the number of ways to arrange X successes and n failures. So I can look at this portion of the formula as the probability of X successes and n failures, really in any particular order, because multiplication is commutative. And this n choose X or n combine X, this is the number of ways to arrange X successes and n failures. Now don't panic. This function is burned into your TI-8384 calculator. So we're going to tend not to work these things out from first principles, but rather use the rather sophisticated TI-83 command to punch out this formula. Let me write that down. The TI-83, or of course 84, does this command. And we'll get into the specifics of it in a moment. Again, let's look at a little bit of a motivating example here. I think we already talked about this earlier. Example. Go back to yellow. Find the probability of 2 boys in 3 births. Well, we've already done this example quite a few number of times. Again, we're assuming boy girl is equally likely in any one birth. All right, I'm going to Well, since I'm looking for two boys here, I'm going to call boy a success. I'm going to let boy be the event of a success. So really I've got a binomial probability distribution here where a boy is a success. I've got 3 births, so I've got 3 trials. There's a fixed number of trials, of course, and the probability of boy-girl is the same, assumed to be the same, in any trial. Alright, so we know the probability of 2 boys in 3 births. Well, in 3 births you've got 8 possible outcomes, and I won't bother to list the sample space here. And as we talked about earlier, if you've got 2 boys, that means 2 boys and 1 girl, and 3 slots available for that 1 girl, so I get 3 eighths, or a probability of 0.375. Alright, let's see if we can get that same result that I got in using a brute force method using the binomial probability formula. Again, this binomial probability formula is burned into our calculator, and this is what our calculator calls it, the binom PDF command. Alright, let me show you where to find this command on the TI-83. Get your TI-83s out and you hit the second level button. Let me get mine out. The gold button in the top left corner. Hit second and the vars button to invoke the distribution command. You're really going to be at that second level. You're invoking that distur button command. And when I hit that second distur command, you'll see a list. Now binom PDF, you have to scroll down to, well, the function address differs from model to model of the calculator. Just be sure to highlight the binom PDF address and hit select or enter to call that command into your home screen. So binom PDF under that second distribution button, and you will scroll down, hit enter to call up the binom PDF command into your calculator. Okay? Alright, now the binom PDF, again, that's the TI-83-84 version of the binomial probability formula. And let me give you the syntax. Now, the syntax goes like this, not very complicated. You've got to plug in an N, a P, and an X. And remember, little n is your number of trials. Little p is your probability of success in any one trial. And little x is the number of successes you're looking for. Okay? So let me work out this above example we did from brute force. It's the probability of 2 boys in 3 births using this binom PDF command. Let's see if we get the same answer. Find the probability of 2 boys in 3 births. Well, I claim this is a binomial probability distribution. You've got a fixed number of trials, 3 trials. The probability of success, a boy, in any one trial is 0.5, assuming boys, girls are equally likely as stated previously. And the number of successes we're looking for here is 2. So go to your calculator, hit second. Above the vars button, there's that distribution command. Call up that binom PDF command into your home screen, and then just enter in 3.5 and 2 for my values of n, p, and x respectively. And if I punch this out, enter it in, I was so busy writing. Binomial PDF, n equals 3, comma, 0.5, comma, 2. Oh, by the way, the comma button is right below the sign button on the TI-83. Alright, once you've entered in all the needed syntax, I hit enter, and guess what? I get the same answer. So the probability of 2 boys in 3 births equals binom PDF 3, comma, 0.5, comma, 2, and that's 0.375. So a very powerful command, and if we scroll up, we see we agree with the answer we got with our brute force method, 0.375. Very powerful, and we're not restricted to such simple examples as 3 births. Alright, well, now that we can expand our horizons a little bit, let's do another example. Find the probability of 50 boys in 100 births. Now, if you try to draw a sample space out for this experiment, you'll be here forever. 100 births, that means there's 2 to the 100th power possible outcomes. So many outcomes your calculator can't even handle it, at least not directly. Alright, so with that powerful binom PDF command, I can say the probability of 50 boys in 100 births. There's a boy there. Well, I'm going to use my binom PDF. Oh, by the way, PDF stands for probability density function. Right. My number of trials, well, I've got 100 possible births here. The probability of boy, if I'm going to call a boy a success, the probability of boy in any trial is 0.5. And my desired number of successes here is 50. So all I need to do is plug in 100, comma, 0.5, comma, 50. Again, your comma button is right above the, or right below the sign button on the TI-83. And let me punch this out. Second vars 0, 100, comma, 0.5, comma, 50. I get 0.079. I'll call it 0.079. Certainly not as simple as taking 50 and dividing it by 100, right? Alright, so again, very powerful command, and can be used to compute probabilities in some pretty complicated, otherwise complicated situations. Get a fresh screen. I want to look at example 2. In our text, example 2 is on page 213, and let's read through it together. You may want to pause and turn there. Let me get there also. Example 2 talks about Twitter. Given that there is a 0.85 probability that a randomly selected adult knows what Twitter is, use the binomial probability formula to find the probability of getting exactly 3 adults who know what Twitter is when 5 adults are randomly selected. So I'm going to call knowing Twitter, knowing what it is, a success. Alright, and I'm wondering what's the probability of 5 adults selected, what's the probability of getting 3 adults who know Twitter, 3 successes. Alright, so I've got 5 adults possible here. The probability of knowing Twitter, that any one adult knows Twitter, is 0.85. That's stated explicitly in the problem. And I want 3 successes. I want the probability of 3 adults knowing Twitter. So the probability that 3 in 5 know about Twitter I'm going to go to Binomial PDF or Binom PDF, and I plug in n, my number of trials, 0.85, my probability of success in any one trial, and 3 for my desired number of successes. Give me a minute to catch up here. Second distribution. Scroll down to Binom PDF. Call the command into my home screen. Enter 5, 0.85, 3. Hit enter, and I get 0.138. And that agrees with the answer in the text. So again, we can see this is a very powerful and really flexible command. You can work out these probabilities by hand, but certainly this powerful command takes a lot of the tedium out from that process. I would now want to look at number 30. I believe number 30 is one of our problems in our homework list. Number 30. And let me turn there. You may want to turn there also. All right. Number 30 on page 220. Live TV. Based on a Comcast survey, there is a 0.8 probability that a randomly selected adult will watch primetime TV live instead of other options. Assume that 7 adults are randomly selected and find the indicated probability. Alright, we got A, B, C, D to worry about. Well, so the number of successes we're looking for is going to change from A to B to C. Alright, let me write down what I'm given here. Well, we're going to be selecting out of 7 randomly selected adults. So my number of trials is going to be 7. Right? And I ask these 7 adults, do you watch TV live instead of online, etc.? Alright, the probability, I'm going to label watching live a success. Okay, so I'm looking for a certain number of successes here in 7. Well, the probability that any one adult watches TV live instead of online is 0.8. And let's see, the number of successes we're looking for, that's going to change. So let's read part A. Find the probability that exactly 2 of the selected adults watch primetime TV live. So here, x equals 2. So the probability of 2 of 7 watch TV live. Well, I can just plug this into Binomial PDF formula. And let the calculator take the brunt of the calculations. I've got 7 trials. The probability of success in any one trial is 0.8. And the number of successes we're looking for in this part of the problem is 2. I punch that out, and I'll call it 0.0043. Answer to part A. Part B. Find the probability that exactly 1 of the selected adults watches primetime TV live. Alright, so here we're looking for 1 success. I want the probability that 1 of 7 watch TV live. Alright, so my number of trials is going to stay the same. The probability of success in any one trial is the same, and my number of successes here is 1, not 2, so I enter in a 1. And I'll punch this out, and my calculator responds in this fashion. I get 3.584 e minus 4. Now, of course, you should be familiar with this scientific notation. Alright, so I'm going to rewrite this number. Remember the rules for scientific notation. If your exponent is negative, really this means 3.584 times 10 to the minus 4th power. Right? This is the Texas Instrument shorthand for scientific notation. And I'll just take 3584. I'll take this decimal place and move it 4 places to the left. 2, 3, 4. Alright, so there is my number in standard notation, not scientific notation. Scientific notation is merely a convenient way to represent very small or very large numbers. So there's my answer to part B. And if you want to leave your number in scientific notation, that's fine. Let's look at part C now. Find the probability that fewer than 3 of the selected adults watch prime time TV live. So I want the probability that fewer than 3 of 7 watch TV live. Well, what does fewer than 3 mean? Well, fewer than 3 means 0 or 1 or 2. So I can reroute that event as the probability that x is 0 or x is 1 or x is 2, because x can only take on whole number values here as number of successes. Alright, these are exclusive events with ors in between. What I'm getting at is you can just add up individually the probability of the 0 case and the 1 case and the 2 case. But the 2 case was the answer to part A. That was 0.0043. And the 1 case was the answer to part B. And the 0 case, well, I've just got to add in the 0 case here, and I'll write it like this. Binom PDF. I've got 7 trials. The probability of success in any trial is 0.8, and we're looking for 0 successes in that first term. That's kind of crowded there. Let me rewrite that. Give me a minute. To these 2 previous answers, I want to add the probability of the 0 case. So I'll just add in Binom PDF, 7 trials, 0.8 probability of success in any one trial, and I'm looking for 0 successes in that case. And I would punch it right in my calculator just like this, maybe save some time. If I punch this all out, I get 0.00467. I believe that's the book's answer. Yes, it is. Alright, so there's A, B, C, and D. They ask us kind of a critical thinking type question. It says, if we randomly select 7 adults, is 2 an unusually low number for those who watch prime time TV live? Well, if the probability of some event is less than 0.5, or 0.05, I should say, we claim that event is unusual. You may recall that language from the author in previous sections. 0.05 really represents a 1 in 20 chance, and that's kind of a milestone that's evolved over the decades, indicating a usual from an unusual event. Alright, so if your event's probability is less than 0.05, we claim it's an unusual event. And certainly this value here, right, if we randomly select 7 adults, is 2 an unusually low number? Oh, wait a minute, 2. What was the probability that x was 2? That was the answer to part A, was it not? And that was 0.004, 0.00430. Alright? So the probability that x is 2 is certainly less than 0.05, this unusual / usual milestone. So we claim that the event that x equals 2 is unusual. Again, by our author's guidelines. And I'm reading the author's answer here for number 30 to part D. It says, yes, the small probability from part C indicates that 2 is unusually low. Okay? Alright. Let's go on. I want to talk about another problem from your homework list. And I believe this is going to be the last one today. Number 37 on page 221. Again, talks about television. Talks about Nielsen ratings. Now let's read the problem together. You may want to pause and get there yourself. CBS televised the recent Super Bowl football game between the New Orleans Saints and the Indianapolis Colts. The game received a rating of 45, indicating that among U.S. households, 45% were tuned to the game. Okay? An advertiser wants to obtain a second opinion by conducting its own survey, and a pilot survey begins with 12 randomly selected households. Right away I know my number of trials is going to be 12. Alright, you're basically asking these 12 people, did you watch the Saints-Colts Super Bowl game? Part A, find the probability that none of the households is tuned to the Saints-Colts game. Alright, well, if we're going to call watching the game a success, the probability of success is 0.45 because we are told the Nielsen share is 45. So that's given to us. Let's look at part A now. Again, X is going to change from part A to part B to part C. Part A, find the probability that none of the households, well, none means 0, right? None of the households is tuned to the Saints-Colts game. So the probability that 0 of 12 are watching this game, well, again, it's a binomial experiment. You've got 12 trials. The probability of success in any trial is 0.45. So I'm going to use my binomial PDF or binom PDF command with 12 trials, 0.45 probability of success in any trial, and looking for 0 successes here. Okay, if I punch this out on my calculator, I get, well, my calculator says 7.66 e minus 4. Remember, in scientific notation, there's 7.66 times 10 to the minus 4 power, and all that means is you take 7.66 and move the decimal place 4 places to the left, and I can rewrite that as 0.000766. So there's my probability of 0 successes in 12 trials. That's the probability that none of the households surveyed is tuned in to the Saints-Colts game. And that's a low probability, and you might think amongst 12 people you're probably not going to have much of a chance that nobody is watching this game. Part B, find the probability that at least one is tuned to the game. Alright, same given information. Want the probability of at least 1 in 12 is watching this game. Alright, how are we going to grind this out? Well, I can rewrite that in this fashion. The probability that X is greater than or equal to 1. That's at least 1, right? 1 or more. And we can go up to 12 here. I can do this. I could attack the problem like this. I could take the 0 case, add it to the 1 case, but I think you can see the problem here. If I attack the problem in this fashion, I'm going to be grinding out my binomial probability formula 12 times. And that may be a too cumbersome way to attack this problem. I think I see a better way. The probability of at least 1 in 12 is watching the game. I claim that's 1 minus the probability that none are watching this game. If we may recall from earlier section, the probability of at least 1 is 1 minus the probability of none. Well, if none are watching, that's really the probability of 0 successes, right? And 0 successes, we already have that from part 1, do we not? It's 1 minus 0.000766. This is the answer to part A. And if I punch that out on my calculator, I suppose 0.999 would be a good enough answer. But since I've got the calculator here, I'm going to be a little more accurate. 0.999234. Alright, so that's part B. Let's look at part C. The probability that at most one is watching this game. Am I going to have some more room here? Maybe not. Let me get a fresh screen. Hang on. Let's find the probability that at most 1 in 12 is watching this game. Well, what does at most 1 mean? That means 1 or less, doesn't it? That's really the probability that x is less than or equal to 1, is it not? And how many values, possible values of x, do I have less than 1? Well, there's only one. That's the 0 case, to which I can add the 1 case. Can I not? Alright, so I'm going to punch this out just like this from part A. I know the probability of the 0 case is 0.00766, and the 1 case, I can grind that out on my calculator. I'll just enter it just like this on my calculator, Binomial PDF. For the 1 case, you're looking at 12 trials. The probability of success in any one trial is 0.45, and you're looking for 1 success here. And I punch all this out, and I get 0.00829. That would be my final answer here. The probability that at most 1 in 12 is watching this game is 0.00829. Let's consider part D, another critical thinking type question. The author asks, if at most one household is tuned to the Saints-Colts game, does it appear that the 45 share value is wrong? Why or why not? Well, they're saying that they're assuming at most one household is tuned to the game. All right? At most one household is watching the game. As we've determined, that happens with a pretty small probability. This event occurs with a rather low probability of 0.00829. Certainly less than our 5% or 0.05 milestone. Right? This suggests that something may be wrong in the assumptions for this problem. This suggests that perhaps the assumption of a 45 share is wrong. Doesn't prove it, but mainly suggests it. And this foreshadows some things we're going to be doing later on down the line. Alright, so 5.3, again, binomial probability distributions, introducing a very powerful command on our calculator and a very powerful formula in general, the binomial probability formula. Alright, we're at 39 minutes, so we're going to call it a day, and this concludes section 5.3 video lecture.